name is Thurman Bridgers. I'm from Joannis Technologies. I'm joined by my colleague, Ken DeMario, and somewhere out there listening is another colleague of ours, Raw Signal, workaholic like we all are. Again, welcome to Module 2 of our Power Monitoring Seminar. In this module, we're going to talk about energy monitoring overview. We'll talk about some of the aspects there. We'll go to our slide here. Just bear with me here. Computer's acting up, but we're on track now. So this is our agenda. This is what we're going to talk about today. Again, I'm Thurman Bridgers of Joannis Technologies. I'm joined by Ken DeMario. Also monitoring remotely is Raw Signal. So we'll be presenting this module. We found it best in doing this to hold our Q&A session at the end. We'll be monitoring chats during the presentation, and at the end, we will answer all your questions. The next module is September 9th, when we get into power quality monitoring. We talk a little bit about overview, standards and terms, rules of thumbs, etc. So hope you can join us for that module as well. In this particular module here, we're going to talk about, we're going to get down to some of the basics, AC versus DC, the relationship between, watts, VA, VARs, and power factor. We'll talk about that. Energy and demand overview. We'll talk a little bit what the aspects, what goes on there. Utility billing. We'll talk a little bit about standards, billing factors, and we also have a case study that we've nestled in here. And then, of course, your questions. And please chat your questions. And again, at the end of our session, we will answer those questions. And again, as a reminder, we will also be recording this presentation, which will be available on our website after a short time. So about Joannis Technologies, those of you that are new to Joannis, we've been around since the early 1960s. You can think of Joannis as really the pioneers as far as power monitoring. We kind of started it all. Where we're located, if you draw a diagonal line between New York City and Philadelphia, Pennsylvania, we're probably somewhere in the middle. So that's where we're located geographically. Our current service and product portfolio, of course, we're known for our three-phase power quality meters and demand instruments, also permanently installed demand, power quality, demand, and energy systems, our analysis software produced by our sister company, Electrotech Concepts. They're known for PQView, which is used by a lot of the utility customers. We're also a master distributor for Gaussian Metrowatt products, and they range from anything from precision multimeters and testers to electrical safety installation and other types of testers, light meters as well. Our tech support is still free. We're known for our tech support. We're known because we have free tech support. We also perform services for remote and commissioning, training, and then of course there's Joannis.com, which is our website. You can go there. There's a host of educational information, case studies, tech tips, product information. And here's a visual of some of our products here. This is, again, it ranges anywhere from permanently installed. If you attended our last segment, we talked a little bit about some of the permanently installed products that we have. We're known globally for our portable instrumentation, and then of course our PC software, both for portables and system software. And I want to pause for a moment here and introduce, we made an announcement yesterday of, let's go ahead and pull up this page here, just bear with me. And we'll go back. Okay. Hopefully everyone can see that. We announced yesterday a new product to the Dranitz line. It's Dran Expert. Again, another product from the legendary Dranitz Technologies. It's known as Dran Expert. It's basically a portable power logger and PQ detector. And here are some of the specifications. And again, this information is available on our website. You can just simply log on to get more detailed information. If you have questions, specific questions, you can always come to us and we'll provide those answers for you. But just going through it briefly, you have sampling rates, the measurement inputs, current inputs, frequencies, accuracies as far as energy parameters are concerned and power parameters. Looking at some of the other things here, these are the various types of connections that is supported by this instrument. The way the takeaway from this is that Dranitz has now introduced a low-cost power monitor PQ detector that we feel will appeal to a lot of the users that are looking for something less sophisticated, but with the legendary Dranitz name behind it. So these are some of the specifications here. Communication interfaces. We can support Ethernet, USB. We support protocols such as Modbus and those that are backneck applications. And here's some of the information as far as the mechanical, environmental, and safety. And again, this information is on our website. Just simply go to Dranitz.com, go to products, and again, you'll come to this page. There's specifications, there's features, and their descriptions. And please don't be hesitant as far as asking any questions that you might have, from pricing to any technical information. All right, so we're going to go back to our module here. Just bear with me. And where is it? We'll go here. All right. We'll just step through here. Okay. So now let's talk about the building blocks to AC power. I know for many of you this will come across as redundant, but every once in a while it's always a good idea to make sure you have your foundation strong as when you approach more advanced problems. And so what we'll talk about is total power, and total power is basically determined via these two methods. The first, which is the square root of 3 multiplied by the current, by the voltage times the current times the power factor. You'll generally find this formula in any of the textbooks today as far as determining total power. The one thing to keep in mind, and what you see here that is highlighted here, that this will hold true for a balanced circuit. So if a balanced circuit, this formula is valid. Most systems that we see is not 100% balanced, so you have to be aware of that. Sometimes we see scenarios where someone has a power monitoring. It can be Dranitz, it can be any other instrument, and it's actually measuring power. It's connected to a circuit with some imbalance, and they're taking the power numbers, the total power numbers, and they're using this formula here, just kind of validate it, and then they see the differences, and they're wondering why we have those differences. And we get those calls all the time where we say, well, the first thing you want to review, what are your currents? Are they balanced? And if not, then really, then this formula here is not very useful for determining power in an unbalanced circuit. So the second formula that you have here is basically the sum of the individual phases. And it's fairly straightforward. So this would account for any imbalance that you might have in the circuit. Incidentally, most meters are using this type of, using this formula here to determine total power. And then of course you have alternating current, or AC to be short. And these are the factors that are involved. It's the power factor. And then you have resistive and inductive and capacitive loads. The one thing to keep in mind regarding power factor, there's basically two different types of power factor. If you think of the old traditional method, which was simply the angle between voltage and current, and then you take the cosine of that, which is known as displacement power factor, DPF. And then, of course, you have what is true power factor. True power factor is just simply the ratio to watts to VA. The reason that is important today is displacement power factor can be easily influenced by harmonics. You have distorted waveforms that can change the phase angle between voltage and current. Therefore, it can affect the power factor, displacement power factor. True power factor is simply the watts to VA, so it's not affected by any harmonics. So that's something to keep in mind. The other little tip as well is if you can determine if you have harmonics on your system, is if you have an instrumentation that is capable of providing displacement power factor and true power factor, note the two values. If they're the same, then there's a very good chance that you have very low harmonics on your system. If there is a discrepancy between the two, then that would indicate that you have harmonics as well. So that's a little tip to keep in mind regarding power factor. And then, of course, if we're viewing it graphically, as far as what does a resistive load looks like versus an inductive load versus a capacitive load, obviously with a resistive load, your voltage and current are in phase, so to speak. You can view it graphically by viewing waveform data, or typically what you would use is a phasor display or a phasor chart. But here we see resistive where they're in phase. Here we see inductive where the current actually lags the voltage, and then the capacitive load where it's just the opposite, it's leading the voltage. So you'll hear the term lead, lag, you'll hear the term inductive, capacitive, so forth. And then, of course, you have the power triangle, which has been around way before I was born. And the power triangle basically shows the relationship between VA, watts, and VARs. Now, there's a couple different ways of looking at the power triangle depending on what your perspective is. From the utility, you might view it one way, the end user is another way. But a lot of the formulas that you see, for example, power factor, cosine of the angle, a lot of these formulas are derived from the power triangle. Okay. We're going to, I think I have a poll here that I want to, okay, why isn't my, all right. So here, I'm going to launch a poll here. And what does power factor correction do? So you guys can go ahead and chime in on this. And we'll give it a few seconds to allow everyone to put the poll here. Give it a few more seconds. We're about halfway through. So we'll give it another 30 seconds. Okay. And we'll give it another second or two. Yeah, we're just about there. Okay. 79%. I guess we can end it now. And give it another second. All right, we'll stop it. All right, so as we can see here that 85%, close to 85% increases power factor towards unity to improve efficiency and save money. And of course, we reduces power factor towards 0 to improve efficiency and save money. So essentially, you can basically say almost 90% increases the power factor to improve efficiency and save money. At the end of the day, it's basically saving money. Let's go on to our next screen here. And yeah, I would say that is correct, but it depends on how you're viewing power factor correction. There's basically two different ways of viewing it. From the end user perspective, and you have to remember that, power factor, what capacitors do, right? They add VARs to the system. So you always have to keep in mind that you have to have a certain amount of VARs in the system in order for things like motors and transformers to operate. So you always have to keep that in mind. From the end user perspective, to improve power factor correction, if you're in a scenario where maybe utility is penalizing you for poor power factor, and generally these days, any power factor that's less than 92% or 0.92 is considered poor. I can remember back in the day where power factors is 85%, 82%, 80% was once considered good. That is no longer the case today. So if you're the end user and you're being penalized for poor power factors, then what do? Well, you have to correct it. And so one way that you correct it is with power factor correction. Now, if you're the utility, then power factor correction is used differently. Power factor correction is used as far as adding VAR support to the system. And that's very important as far as voltage support. So it depends on from which perspective you view power factor correction. You have the end user, and then of course you have the utility. Here's our second poll here. Which caused this power quality event? And I'm going to go ahead and launch the poll here. Just bear with me here. We'll launch it. And so we'll wait. I think the poll is in process here. And we'll give it a few seconds to allow the information to come in. We're about half. So we'll give it another couple seconds. We're about 2/3 there. All right. I think we've waited long enough, so let's see the results. So here's our results. Hopefully, can anybody see that? Let's share the results. All right, so by far, absolutely, power factor correction, capacitor switching is what caused this event. Now, from a power quality perspective, and this is something that we're going to cover in subsequent modules, this is probably one of the most common type of events that can cause things such as nuisance tripping on VFD loads, UPSs, things of that nature. We'll talk a little bit about those things in the later modules. But yes, power factor correction is by far the cause of this event. And this is your classic power factor correction switch and transient. So those of you that are into waveform analysis and you have the instrumentation capable of recording the waveform data, there it is. That's you can't get any more classic than that as far as capacitor switching. All right. All right, let's talk a little bit about demand and energy, because the two are different. There's demand, and then of course there's energy. Demand. Let's see if we can stop this poll here. All right, thank you, Ken. I got a little bit ahead of myself. Apologize for that. So let's talk about demand and energy. These are the two major factors on a utility bill. Demand, It's usually measured in kW. It's the amount of power that's averaged over a certain interval. The interval can be 10 minutes, 15 minutes, or 30 minutes. Here in the US, a typical demand interval is 15 minutes. Energy is pretty straightforward. It's basically watt hours, or you'll hear kilowatt hours, or you may hear megawatt hours, and it's just simply accumulation of power over time. And for example, 1 kilowatt for 1 hour equals 1 kilowatt hour. So it's pretty straightforward, and it's basically the bulk of our, if you're a residential customer, that is the bulk of your bill is kWh kilowatt hours. Well, conversely, for an industrial or commercial customer, or let's say a non-residential customer, demand makes up a big part of your utility bill. So to view both graphically, what you see in this slide here, the top graph is pretty much a plot for energy usage, kilowatt hours, megawatt hours. And you can, because it's cumulative, it's going to start at a certain value and it's going to be accumulative until when you go read the meter, for example. An example is your meter, kWh meter on your home. You know, whether it be one of the new static meters or whether it's the old electromechanical meter. You know, if you were to go out now, well, I don't want you to go out now because you're in this webinar, but if you were to go out as, let's say noon, for example, and then read what the value is for kWh, and then you go back out, let's say at 5 p.m., and you read it, you're going to have a new value. So basically, it's an accumulation. And simply, if you want to determine the usage for that period, you just simply take the delta of the two readings. And that's basically how kWh's kilowatt hours is recorded. Now, demand is a little bit different because demand, what we do is we take active power. Some people refer to it as instantaneous power, but it's the active power that is averaged over a specified interval. So whether that interval is 15 minutes, 30 minutes, or 10 minutes, you will have what is called your demand. For example, these curves here, this is typical of a facility where you can easily determine the workday, the daily workday, the weekend, and then of course the subsequent week. Obviously we see where the weekend is. Each of these data plots here that makes up this curve is that 15-minute interval in this case, which is the demand. And then just going back here, for example, these slopes that you see here, that's what's known as the energy rate. So the parallel that I can draw to that, those that you are familiar with the old electromechanical energy meters, kWh meters, that have the spinning dial. That spinning dial represents the energy rate. So if it's spinning very slowly, you're accumulating energy, but you're accumulating at a slower rate. If you happen to have everything on in the house, like in my household, people can't turn things off, you know, then that dial is spinning very fast. So that's what these curves here kind of represent, these slopes. It's still accumulative, but depending on how steep or how shallow, that indicates the energy rate. So let's talk about utility billing. There are metering standards. You basically have two. You have the ANSI standard here in the US. You have the IEC, which is Europe and other parts of the world. The two kind of sort of parallel each other. They kind of want to keep up to date with each other. For example, the ANSI standard is widely accepted by the industry as far as for revenue metering. And of course, there's the IEC standard that is the same as well. So you have the different requirements for electrical, and for example, the IEC standard. You have the general requirement, you have category for electromechanical meters, and of course the static meters. And then of course the ANSI, the code is for electric metering, and then you have the ANSI C12-20, which basically defines the accuracies and performance requirements, calibrations, etc. And like I said earlier, these standards are widely used for revenue metering. So in the industry, you always hear revenue certified versus revenue accurate. And simply the difference between the two. As far as the standards that they comply to, they both comply to the ANSI and IEC standards. So if you have metering that is compliant with those standards, then technically the meter is suited for revenue metering. The difference between revenue certification and revenue accurate is with revenue certification, you have a third party. You have a third party that certifies that meter for revenue metering. There are certain applications in which it's a requirement. There are certain laws which says that you have to be revenue certified. But if you're comparing apples to apples, accuracies to accuracies, because they both are compliant with ANSI and IEC, just because I have a meter that may not be revenue certified, if the application or where I'm going to use it does not require revenue certification, I can certainly use that device for revenue metering. So that's the behind that. Let's talk about utility billing, because there's many factors that go into the utility bill. Of course, you have the two main contributors, which is demand charges and energy charges, but you also have power factor penalties. If you're being penalized for poor power factor, that you will incur power factor penalty charges. There's such thing as ratcheting. There's fuel surcharges. And then you have other costs, delivery costs, and things of that nature. Just look at your residential utility bill. You would think that KWH, you just be billed for that, but if you look at all the other factors that are on the bill that contributes to the total. So the same here as far as utility billing. Demand charges, and this is typically how a demand charge is calculated. And again, demand is basically active power. Some people call it instantaneous power. The technical term is used as active power. So the active power is averaged over a specified interval. And again, here in the US, 15 minutes is the typical demand interval, but the interval might be different in other places of the world. But essentially how it works here, if we look at this chart, we see for the first 5 minutes, our active power is 100 kW. Then for the next 5 minutes, the active power is at 400 kW. Then it goes to 1,000 kW. Well, if you take the average over a 15-minute period, it comes out to be 500 kW. And if that is the highest demand interval, a lot of the instrumentation meters, demand meters, or instrumentation that is capable of providing demand data, what they do is they keep track of the highest demand interval of the billing period, and that becomes your demand charge. There's even instrumentation that will simply maybe keep track of the 4 highest demand intervals. But from the utility standpoint, it's the highest demand interval of the billing cycle. And the billing cycle might be 30 days, typically it's 31 days. So that value is put on a tier. So for example, let's say if your demand charge was your highest demand interval for the month might have been 100 kW. Well, then your pricing might be somewhere along the lines of $7 per kW. I'm just throwing numbers out there. Might be $7 per kW. But let's say from 100 to 500, and your demand falls within that window, then the price per kW will go up. And so the higher your demand charge is, the higher your price per kW would be. So that's basically how the utilities derive your demand charge, your bill. Energy consumption, again, is pretty straightforward. It's consumed in watt hours. Um, yes, it's typically smaller than demand charges, unless you happen to be a residential customer where you don't have a demand charge per se. You basically are charged on usage, kilowatt hours. You also have what is called time of use, and this is important because the cost per kilowatt hour is different depending on when you use it. For example, your cost is going to be at its maximum for on peak, and on peak might be from 8:30 to 8:30 a.m. to 5:30 p.m. or to 5 p.m. Monday through Friday, where you actually pay more per kilowatt hour. Mid-peak, you would obviously pay less. Off-peak, you would pay less even still. So part of any energy management program, if you're monitoring the energy, then you want to get an idea of how much you're using during on-peak versus mid-peak versus off-peak. And it might be a matter of, if I'm doing a lot of the processes doing on peak in which the price per kilowatt hour is at its premium, are there options for me to shift those operations to mid-peak and off-peak times in order to save money? So, any part of any energy management program would usually have time of use, so you can keep track of where you're using the kilowatt hours. So in this case study here, we're going to inject this case study, and we're comparing a compact fluorescent and LED bulbs and the old incandescent bulbs. We're comparing them side by side. Do they provide the energy savings as advertised? And we can identify with this at a residential level because we have these devices in our homes. Either we have LEDs, or we have incandescent, or we might have a mixture of all three. Me personally, I went in and ripped out everything, and I have LED bulbs now. But so here we did a side-by-side comparison, and viewing the active power. Here we have our trends here. This is the incandescent bulb. This is the compact fluorescent bulb, or the CF bulb, and this is the LED bulb. So we can see from an active power trend that this is 60 watts. This is about 10 watts, 12 watts. This is probably around 10. So we can see from an active power standpoint that they're pretty much match the nameplate information on the bulb itself. And then, of course, now we're viewing it from a different perspective. Here we're viewing the energy consumption. And remember, your typical energy plot is one of, especially if it's a accumulated plot, is one that you basically have this diagonal trend. And remember, it's accumulative. So we're going to start at a certain time. We're going to accumulate until we stop. And then basically the difference between when we start and when we stop is the amount of kilowatt hours that was used for that period of time. So in looking at the three, we can obviously see that the incandescent bulb uses more energy. We see that the LED bulb is of the three uses less energy. You can see that the energy rate is fairly constant. There's no dips, or there's no, I would say, peaks or valleys. So it's fairly constant. I should say the energy rate is fairly constant between the two. So obviously, in viewing this particular graph here, if one was managing energy, cost savings, things of that nature, then the choice would be our LED bulb, because it clearly shows here the reduction, the energy reduction here. So if we did a summary of this, our incandescent bulb, 60-watt incandescent bulb, You can see that the bulb cost is about 55 cents, the cost to operate it. Okay, and then we compare that to our CF bulb, and again, the cost to operate it. And then, of course, the winner of this particular case study is the LED bulb, as far as its cost, the bulb cost, the annual cost to operate, and so forth. And we can see from this slide here that the math works. And again, you know, the obvious choice here would be the LED bulb is from an energy savings standpoint. Now, poll number 3, I think this is more like a tease here. Does the energy efficient lighting cause PQ concerns? And the answer to that is I guess we can call this a tease, right? So attend our next virtual seminar on September 9th. And of course, we will dive into this a little bit more. You know, the philosophy here, my philosophy is always power monitoring. I try not to segregate the two, energy versus power quality. I tend to look at the big picture, especially with energy. You can have energy cost savings methods in effect, and you're monitoring the energy, and you know where every kilowatt hour is going, and you have it managed perfectly. But if you're not watching the power quality, you can have a single power quality event that can come along and basically delete any energy savings that you might have accumulated. So it's always a good idea, if you have the instrumentation, if the instrument is capable of providing power quality data, you should always be monitoring the power quality as well. And we'll get more into the power quality aspects of it at our next virtual seminar on September 9th. And again, just to review, Drainage monitoring products from handheld to permanently installed. And again, don't forget to, when you have time, go to our website, go ahead and view the detailed information on our latest product introduction that we introduced yesterday, the Drain Expert. I think you'll find its specifications very useful for your applications in terms of versatility and cost. And again, if you have any questions after this seminar that happen to come up, you can always reach us at 1-800-DRANTECH. And I thank you for your time, and we're going to hang around a few and address any of the questions that you may have chatted during the seminar. And let's see, let's go to our chats here. All right. All right, so we'll go back and just reviewing the questions here. All right. So the first question here that I see, make sure that no one answered it. Okay, is there an ANSI standard that defines metering intervals and how the interval values are calculated at the revenue meter? The ANSI standard that I'm familiar with is the ANSI standard 12, ANSI standard C12.20, which I believe will define metering intervals and how the intervals are calculated. So it's ANSI standard. And you know, there's two ANSI standards. There's the ANSI standard, which is C12.1, which basically describes electric metering. And then there's the ANSI standard, which is ANSI C12.20, which defines the meter itself or device itself, which covers you know, things such as metering intervals and how the intervals are calculated. And I think that's the only question that we have. So again, I'm going to remain here for the next few moments, and any questions that that you guys may have. I still see there's a fair number of people out there. So if you have questions, please don't hesitate to chat them over.